Okay, we'll cover Chapter 18 now, dealing with electric currents and light bulbs. Essentially going to introduce some things that you're already kind of familiar with, electric battery, or power source if you will. Idea that we can have electric current, which will be flowing electrons in a circuit. There's going to be things that impede the flow of this current, and we're going to call these guys resistors. Talk about intrinsic property of different materials, its resistivity. Electrical power, how many watts we're drawing. Power in household circuits, and since our household is powered by 120 volt AC current, we'll talk about alternating current, and then I'll just talk very briefly on a microscopic view of electric current, and we won't really spend a whole lot of time on these guys. So, kind of what the heck is an electric battery? I kind of think of it as what's going to be a charge separator. And essentially this fell around 1800 or so. Alessandro Volta, Italian physicist slash chemist, found out that if we had a acid or an electrolyte with lots of free ions, and we stick a couple different terminals in here that are made up of different materials, that this sulfuric acid is going to react differently with this zinc electrode and this carbon electrode in such a manner that we're going to, from the chemical reaction, free up positive charges on the carbon and negative charges on the zinc. Now, I'm not really a chemist, so I don't care too much about the chemistry of what's going on here. Again, all I care about is that we can separate out charge using a simple battery. Keep in mind that energy cannot be created nor destroyed. This electrical energy created by the charge separation actually comes from some chemical energy, so it's not like we're just kind of creating energy. And the nice thing about a battery is that the potential difference is going to be maintained even if some of that charge is flowing off of the battery terminals pretty much until one terminal or the other is completely dissolved by the acid eating away at it. So let's kind of take a look at what a battery does. As I've said, what I really care about is that it's going to be a charge separator. And now let's kind of see what's going on here. First of all, nowadays we don't use sulfuric acid. Now we use kind of a paste that's not going to spill everywhere if you cut a battery open. So imagine getting sulfuric acid all over the place, not a good thing. My kind of heuristic view of a battery is to kind of think of it as an elevator for charge. So suppose I have on the negative terminal right here, I have a positive charge, and this positive charge is attracted to the negative terminal. What the battery does is it gives up some chemical energy, and it acts kind of like an elevator and pushes this positive charge up to the positive terminal. Again, it doesn't like those other positive charges, it feels a force away from them, but the work done by the battery is able to overcome this through that chemical reaction. Now at the end of the day, what we're going to end up with is, say, some voltage down there, we'll call that our 0 volts, and then we're going to have some potential up here. Again, we only care about VAB, the potential difference between A and B. So here I might have a potential of 0 volts, and here I might have a potential of 1.5 volts. Now what I can do is I have the ability to actually do something. Now I can say, hey, I can make this charge flow. One thing about taking two batteries, suppose here I have a voltage of 0 volts, here I have a voltage of 1.5 volts, is if I stack another battery on top of it, it's kind of like doubling the size of this elevator. So now here, if this is another 1.5 volt battery, I would have a potential of 3 volts. So now I've got my charge right here, and if I provide this charge a pathway with which to flow, then this charge can flow through this light bulb and come down back to the negative side of the house, which the positive charge is actually attracted to. So now we know that batteries kind of act like just kind of elevators that take positive charges and move them up to the very tippy top of the battery. Now again, if I provided some path with which this positive charge to take, then I'm going to have kind of a flow of charge. This flow of charge has a special name. It's actually called the current, and we would say that the amount of current is going to be how much charge is flowing by in a given amount of time. You can kind of use a river analogy. Say here I've got some riverbank and I've got some water that's kind of flowing down the river, well, heck, if I say how much water is going to flow by this this little checkpoint in some given amount of time, that's the current in the river. So also is defined the amount of current flowing through a circuit. We're looking at the amount of charge per unit time, and the coulomb per second is also known as the ampere or an amp. So we'll talk about how many amps are flowing in our circuit. Now, just a couple of things to note in this on the slide here is if we want charge to flow, we need to have a complete circuit. So we need to go from the positive side of a battery all the way to the negative side of a battery. We could also say, hey, this guy's kind of messy to draw. Let me draw a nice little schematic with nice, neat, kinked little lines here. I don't necessarily need to draw my battery. Can draw two lines like that where I have a positive side of a battery and a negative side of the battery, so that's going to be my battery or my power source. I don't have to draw weird squiggly lines. I can just kind of draw straight lines. I don't need to draw my light bulb. I can just kind of draw a box and say device, and a little bit later I'm going to make that a sign of a resistor. And something to keep in mind is that it comes all the way back to the negative side of the battery right here. The direction of current flow is going to be fairly important, and the way that I always kind of remember it is take a look at this positive side of the terminal. It's going to be flowing away from that positive side and towards the negative side. And again, just to really highlight it, we must have a path from one battery terminal through the circuit and back to the other battery terminal. So if you take a look at A, B, and C, only one of these circuits will actually work. Here we have the positive battery terminal, so it's just kind of touching this guy right here. It's going to give it a positive potential, but nothing's going to flow. There's no path to this negative terminal. Kind of the same is true for this one. It's going to put some potential on both sides of this light bulb, but it's just going to be some constant potential, some charge just kind of hanging out there. There's no way to get down to this negative terminal. This one right here, charge can go up, flow through the battery, come out the side of the light bulb, and work its way down, and this light bulb will actually be the only one that can possibly light up. Now, there's one thing that's kind of confusing about electric current, and that's going to be the direction. Essentially, you can blame this on Benjamin Franklin. He's the one that discovered the fact that we had positive charge and negative charge, but he actually named electrons to be positive while it was actually vice versa. So when we talk about conventional current, we typically define that to be going from the positive to the negative. So if we look at our battery, we're going to say that our current is going to flow around the circuit in that direction. However, keep in the back of your head, what's really going on is we're setting up an electric field inside of this wire. The electric field is going to point in that direction right there and kind of come in right here. Now, electric field, or the electrons, remember F is equal to charge times electric field. Electrons are negative. Electrons are actually the thing that are doing the flowing, not the positive charges. Positive charges tend not to flow. Electrons do all the flowing. So this electron is actually going to feel a force in the opposite direction because it's negative. And so the electrons are actually flowing in that direction right there. But whenever we talk about current, more often than not, we're talking about conventional current. So just kind of keep in the back of your head that electrons are the ones that are actually doing the flowing, not the positive charges, but they're simply in the opposite direction. Now, kind of coming back to my water analogy, if we think about how much current is flowing, it's actually going to be proportional to how much potential energy it has. Kind of think if I took a rock and I moved it to the very tippy top of the hill, or took some water and moved it to the very tippy top of the hill, how fast it's going to flow down is going to depend on how high the hill is. Same is going to be true for conventional current. Suppose I take a positive charge, I move it to the top of a battery. How fast it's going to tend to flow is going to be related to how high I lifted it up. Now, the question is what if there are rocks in the path? What if there's some resistance? So now, suppose I put a whole bunch of rocks in there. Well, kind of in your mind's eye, you'd say, well, there's a lot more resistance going down this hill right here, and so this water is going to tend to flow slower, and that is the case. The same is also going to be true if I kind of put, metaphorically speaking, rocks in this current path. If I put some loads then the current is going to flow slower the more resistance I put in the path. So this leads us to our first major equation here. Make sure we star this guy. It's called Ohm's law, and it relates the potential, the voltage, to the current, as well as the resistance. And you can kind of see right here that potential is going to be the product of current times resistance. If I increase the resistance for a given amount of current, say just 12 volts, then the current must correspondingly decrease, much like you'd expect from the water analogy on the last page. Now, in many conductors, the resistance doesn't depend on the voltage across it, and so it's going to follow Ohm's law. So if I were to plot the voltage on the y-axis against the current on the x-axis, I would kind of expect the slope to be the current, and I'd see kind of a nice straight line right there, where this slope would be equal to the resistance. So I would call this an ohmic device. A material that the resistance changed with voltage, maybe it does something like this. It's not going to have this nice neat slope. It's not going to follow Ohm's law. So this bottom one is what we would call non-ohmic. Now, this creature of resistance is going to have a unit you can kind of see of a volt per amp. I said resistance is going to be equal to voltage divided by current. A volt per amp is also known as an ohm, kind of by that symbol omega. So we'd say that 1 ohm is going to be 1 volt per amp. Now, essentially we use resistors in pretty much any electric circuit that we have. And how do real-life resistors look like? Well, you might want to put a star on this page. Is we identify them with color codes to indicate the value of their resistance as well as their precision. So kind of as you look down a resistor, the bottom of it's always going to be usually a gold or silver band. It's going to be the tolerance. On the opposite end, you're going to have a band that's going to be the first digit, band that's the second digit, and then the multiplier. So you can kind of see right here that our first digit is red, and that tells us that the first number we want to write down is going to be 2. Our second digit is going to be green, so we're going to write down a 5. The multiplier is yellow, so this yellow guy right here has got a multiplier value of 10 to the 4th. So that tells me that my resistance is 25 times 10 to the 4th ohms. Now the tolerance of this guy, it's got a silver band, so it's going to be plus or minus 10%. So that's kind of how you read these resistance bands. Now just kind of some clarifications on some of the stickier points of this up to this point. Now batteries are going to maintain, for all intents and purposes, a constant potential difference across them. If we hook them into a circuit, then it's always going to be 12 volts. The current in a circuit is what's going to vary, and the current's going to vary depending on the potential and the resistance. So I could, kind of rewrite this guy to say that the amount that the current changes by is going to depend solely on the resistance. We can't do anything about the voltage of the battery. Now, resistance, I'll talk about on the next slide, is actually a property of the material. One thing about current is it does have a direction. We know that it is going to always flow from this positive terminal to the negative terminal. So it does have a direction, but it is actually not a vector. So something just kind of keep in the back of your head. Now the last thing to think about here is current and charge don't actually get used up as they flow through a circuit. Whatever goes in one end is going to come out the other end of a circuit. You can kind of think of, suppose I had a water pipe right here and I've got some water flowing through it. If I've got 4 droplets of water that go into my water pipe, sure, there could be some resistance in there, but at the end of the day I still got 4 water droplets coming out of there. So charge does not get used up and current does not get used up. The current over here must be equal to the current over here regardless of what happens inside of this pipe. Same thing's going to be true for current flowing through wires in a circuit. Now it turns out that wires that are, say, made of the same material and they have different lengths or different areas, they're going to have different resistances. And what we can kind of do is we can write the resistance as a function of some constant, its resistivity, which is going to be a characteristic of the material. So for example, copper is going to have some resistivity, aluminum is going to have another, silver another, and so on and so forth. So this is a property of the material itself. All copper will have the same resistivity. All aluminum will have the same resistivity. Now you can kind of conceptually see, hey, if I've got a rod that's this long, it's got some resistance. If I double the length of my, well, I said rod, but wire, then I can essentially double the resistance of it. If I were to say, hey, you know what, I'm going to make this rod the same length, but I'm going to increase its area, what I'm doing is I'm giving more room, for all intents and purposes, for the charges to flow, so that's going to decrease the resistance, kind of thinking back to the water pipe analogy. So it's going to go inversely dependent with the surface area. And table 18.1 just shows you the resistivity for several different materials. So here we have the resistivity. The units are designed such that it'll work out. And you can see that silver is different than copper. That's going to be different than tungsten that you see in light bulbs, iron, so on and so forth. You also can kind of see a temperature coefficient, and what that means is this resistivity is actually going to change just a little bit with temperature, and I'll talk about that on the next slide here. So if you think about circuit design and stuff like that, actually, you run current through a wire, it's actually going to heat up a little bit. And so what we have is we have a changing resistivity. This resistivity is actually going to be a function of temperature, and it's going to be the initial resistivity at some known temperature that we have in the table back there, and then its the operating temperature, as well as that coefficient from the table right there. So if we know what the original resistivity was, and we know what temperature we're driving a wire at, and we know what temperature that this resistivity came from, it should be pretty simple to calculate the new resistivity as we change the temperature.